Okay, we're on our bike for the last question, which is 0654 paper 41 from summer 2018. Okay, we've got a bike. This may be something you've experienced yourself. The bicycle X has a black saddle, bicycle Y has a white saddle. The saddle on bicycle X gets much hotter than the saddle on bicycle Y. Now, as soon as you see the comparison between black and white, you should be thinking one word, which is radiation. Key word, yeah. That's what the only thing that this could really be referring to is to do with heating by radiation. And what you should be aware of is that, say on a sunny day, the road becomes very hot. Why does it become very hot? Well, it's because the road is generally black. Black things are very good at absorbing sunlight, i.e. they are good absorbers of radiation, and therefore they heat up quickly. That's exactly what's happened here. The bike seat, has a black color on the left-hand side in X, and therefore is heating up very quickly. This white one is reflecting the sunlight and therefore not heating up. Okay. Then we've got a bike with a rear lamp A and a front lamp B powered by a battery. Okay, so somehow they're connected up by a battery. Never seen this arrangement before, but we'll see. Okay, key point, they are connected in parallel. Alright, we're being asked to calculate the resistance of these two guys. Okay, we'll just remember that they are in parallel. Alright, we've got a resistance 8 and a resistance 16. Well, in parallel we use this equation 1 over RT equal 1 over and 1 over RB. 1 over RA is 8, RB is 16. We've got 1 over 8 plus 1 over 16. Well, 1 over 8 becomes 2 over 16. Plus 1 over 16, we've got 3 over 16. Now, don't forget the last step here, right? A lot of people do this. Okay. Make sure that you flip this thing, because you know 1 over RT. 1 over RT is 3 over 16. So therefore, RT divided by 1, if you like, is 16 over 3. 16 over 3 is 5.33, which is our answer here. Okay. We're also we know the resistance of this thing, right? Lamp A is 8 ohms. We're not using this 5.33. Okay, we're using the resistance of lamp A. We're told the voltage. All right, we're told that we are using a circuit which has a 9-volt battery. And because they're connected in parallel, we know the voltage across these is the same. All right, so if I know that this is 9 volts, this is 9 volts, and this is 9 volts as well. V equal to IR, Ver. All right, if you like. Okay, our triangle again. Can you see that I'm trying to remember to do the triangles, even though I never really use them myself? V equal to IR. Okay, therefore we want to know I equal to V over R. 9 divided by 8, 1.11 amps. Here's our old friend, the electromagnetic spectrum again. Okay, again, I've seen this now. I think this must be the 4th or 5th time I've seen this going through these past papers. Very common thing that comes up. You are being asked to place visible light and infrared into the spectrum. Okay, again, I won't go through this in detail because I have done this a few times now. At the visible end, you've got violet, and then at red at this end. Okay, we're going in increasing wavelength from left to right. Okay, this way, lambda is going up. Violet has a short wavelength. Red has a longer wavelength. Ultraviolet is next to violet, unsurprisingly. Infrared is next to red. The two that we aren't asked to do, but I've included them anyway, we've got X-rays and radio waves. Okay, last bit. We've got the speed of infrared radiation, 3 times 10 to the 8. We've got the wavelength, which is 715 nanometers. Now, this is where they've told you a bit of extra information. I don't know if we've really used this that much here. But remember, nano, milli, micro, they're all prefixes. They're all representing powers of 10. In this case, it's 10 to the power of minus 9. Okay, so we've got to think about our what that really means and how we put that in our equation. The way you do this is you remember that we are always working in SI units, which are meters. So if you've got 750 nanometers, then what you have really is 750 times 10 to the minus 9 meters. After that, it's a case of using our equation, V equal to F lambda. speed is equal to frequency times wavelength. Well, again, if I have to rearrange to find the frequency, then that is just the ratio of v over lambda. I've got 3 times 10 to the 8, I've got 750 times 10 to the minus 9, and then I've got 4 times 10 to the 14 here. Quick point is that in the electromagnetic spectrum, visible light and infrared and ultraviolet all tend to have a frequency of around about 10 to the power 14. So if you're getting that kind of number, it sounds very big, don't worry about it. Last bit, just a gentle finisher off, alright people, it's a guess of alpha, beta or gamma, hopefully not a guess because we should be informed. Okay, we've got gamma radiation may be released, alpha particle, beta particles may also be related. Which one is most ionizing? Well, remember, most ionizing means worst penetrating. Worst penetrator, okay? So therefore, it means lots of ionization interactions will occur, and hence the particle won't get very far. The one that doesn't get very far is absolutely alpha, okay? Alpha, remember we had this setup where we had paper, we had aluminium, and then we had lead. Okay, we had paper, aluminium, and then PB lead. My alpha gets stopped here, my beta passes through to here, and my gamma goes really all the way through, to be honest. Okay, alpha is the worst at penetrating, and therefore the most ionizing.